and we'll get going. So this month we have our own Jen Mitchell. So Dr. Jen Mitchell, who is a planetary scientist here within the EM Centre. As we all refer, she looks at very cool space rocks, otherwise known as meteorites, but she's a planetary scientist who uses quite a wide array of the equipment we have here, and she's going to talk essentially about her research. So I shall pass over to Jen.
Hi everyone, thank you for coming. I will start sharing this and hopefully it will give you the right slide. Yes, great. Yeah, so like I said, I'm Jen. I work here in the lab. I handle all things sort of rock related, but in my own research and in my own time, I use electron microscopy to analyze meteorites, which is a little bit of fun. So planetary geology is basically the study of planets, moons, asteroids, meteorites, and that can be done through ground-based or probe-based, rover-based sort of analysis, but we can also do physical analysis by using meteorites. So even though we can't physically go to other planets, we can look at things that have come from them and make inferences about that. And the reason we study meteorites is that they provide a really unique window into the early solar system. So it's recording everything from the very first solids all the way through planetary accretion, differentiation, magnetism, the start of geology being geology. And in some cases, they also record the complete destruction of other planets. And it gives us sort of a little window into the inside of core formation and what cores of planets are actually made from. There's over 45 different meteorite classes. And it's a whole range of textual and compositional differences. And they're broken down into this, where we have our chondrites, our primitive achondrites, evolved to achondrites, stony ions, and ions. So there's a lot happening. Each of these individual little classes all has its own set of even further small classes. So it's not surprising that people tend to pick one group of meteorites and focus on that. So I work on these ones, the HEDs, howdites, eukaryotes, and diogenites. And within that, I focus mainly on diogenites. If you try and do all meteorites ever, it's just a little bit too much work, really, I think, for everyone. So I'm going to introduce you to sort of like the basics of Meteor Ethics, try and put some of the stuff that I do in context for you. So like I said, meteorites record the very first solids. So some meteorites include these big white fluffy things here. These are calcium aluminium rich inclusions. We call them CAIs. So these are preserved in carbonaceous chondrites and record a really, really complex evolution. These are multiple stages processing, really high temperatures, and they're composed of a lot of different minerals, including an orthite, which is a type of feldspar, through to melilite diopside, it's a type of pyroxene, spinels. And it's typically associated or accepted that the age of CAIs is what we consider the age of the solar system to be. So the age of the solar system proper, not just the nebula, which predates them, but basically when things started becoming solid and sort of physical processes started becoming dominant. So these have been dated to 4.568 billion years, give or take a little bit. That's through lead to lead dating, because no other isotope system lasts long enough to actually date them. Along with CIs, we also get chondrals. These are spherical grains of olivine and pyroxene, give or take some feldspar. And because they're forming in a zero gravity environment, they form these nice little spheres, which are really, really noticeable. And you don't find them in terrestrial rocks because Earth has a significant amount of gravity. You don't get these really anywhere else. A wide range of textures, you can see it along the bottom here. Everything from sort of like these big chunky porphyritic grains, to like these nice sort of radial sort of vesicular grains, and these fully crystalline ones as well. And importantly, these are really, really susceptible to metamorphism, so they can record a lot of processes once they sort of clump together into rocks. But how you even make chondrals is still very much up in the air. So there could be anything from condensation in the nebula, there could be impact droplets, could be nebular lightning that causes them to fuse together, could be outbursts from the early sun, could be shock waves from the protoplanetary disk itself or from other supernovas. Realistically, it's probably a combination of the lot. And thankfully, I don't specialize in chondrites, so it's not my job to work out where these tiny little blobs come from. If you stick enough chondrals together, eventually you end up with a chondrite. These are the most common sorts of meteorites. They make up over 85% of all meteorites that we have. In the inner solar system, we have enstatite, which is a type of pyroxene, and the ordinary chondrites. They're called ordinary because they are the most common, and there's nothing particularly spectacular about them. And these represent non-differentiated bodies. So these are ones that are bodies that aren't big enough to properly melt and become sort of like a large asteroid or a large planet like you would consider Earth to be. These can be anywhere from completely pristine, where it's just chondrules sort of like loosely packed together, all the way through to the verge of melting. But in the outer solar system, it's a little bit more exciting. We get these carbonaceous chondrites, and these are where we find those CAIs, and you can see quite a few of them in this meteorite down at the bottom here, all those big white fluffy things. I think this is a picture of I think it's a CB3, so quite probably one of the older carbonaceous chondrites. And these record aqueous alteration. So there's not very much water in the inner solar system, but the further out you go, the wetter things get. And there's also low temperature alteration. So there's a whole range of alteration products in these rocks we don't see in these ones. CI chondrites, these are probably the most primitive. These have the same composition as a solar photosphere. So we assume they were sort of the very first sort of rocks that were forming. And if you remember the meteorite that fell last year, Winchcombe, that's a CM2 brachia. And we've been very lucky here in the lab to be part of the team that's working on it. But the most important thing is that carbonaceous chondrites, not only do they contain water, they also contain organic compounds. So it's thought that the inflow of material from the outer solar system may be one of the reasons why we've got life on Earth. So chondrites record a whole range of things. I said they can be pristine up to the verge of melting. And we categorize them with a little number. So 3 is pristine, 1 and 2 refer to aqueous alteration. But basically 3 is your starting point. This is as pure and as clean as a rock can get in space. As they melt, they move into type 4s, type 5s, like this one, and type 6s. We can start seeing this lack of chondrules. So there's still a couple left in this type 5. But by the time you get to a type 6, there aren't really any of those nice big round splodges that you see in the earlier ones. Now, this is basically a recrystallization process. The temperatures are getting high enough for things to start recrystallizing. And this could depend on how deep that particular rock was on the parent body, the size of the parent body. It could be impact heating as well. Because the main thing about planetary science is the temperatures that we're dealing with were much, much hotter. In the early solar system, there was lots of aluminium-26 and other short-lived radioisotopes. The temperatures just generally were really, really high. And if you keep melting your chondrites, eventually you hit these type 7s. And these are quite a new sort of group of chondrites. And these are the turning point from chondrite to achondrites. And achondrite is just a rock that's melted enough that no longer has chondrules. It's very, very, very scientific. And these type 7 chondrites, you can see there's not really any chondrules visible here. These are some EPMA maps. But we're also starting to get these melt networks forming. So all this sort of yellow stuff that's labeled with PL, that's plagioclase. You can start seeing how it's connecting these, all these sort of little groups together. You get these consistent sort of melt networks of plagioclase forming. Now, if you keep going with that heating process, eventually you hit your primitive achondrites. So these are achondrites, they're fully igneous, fully magmatic, but they have the same compositions as chondrites. So we know they came sort of directly after chondrites did. This is an example of some data I collected during my PhD for my PhD supervisor, Andy Tompkins, which has been published actually, which is a nice little surprise to me. This is from a meteorite called the Quadja. It's a Polish meteorite. It's an enstatite achondrites, all these big red grains are just chunks of enstatite. That's a really magnesium-rich pyroxene. And not only do we have these plagioclase meltworks in blue, we've also got a metal sulfide melt network. So we're actually recording core formation in a single rock. And this meteorite itself was maybe only a couple centimeters across, but we've been able to capture a plagioclase melt network moving upwards, as well as a metal sulfide network moving downwards. And this is the start of like planet building proper, if you will. This is the start of core formation. And this happens in, I think, bodies anywhere above sort of, I think the last estimate I read is anywhere about 20 kilometers or so can start generating cores. So you can actually build a planet using not very much material. Then we move into achondrites. So this is basically achondrites that have undergone melting and differentiation, and their melts have started to evolve a little bit. We can break them down into stony achondrites. These include things from the moon, things from Mars, things from large asteroids, as well as a couple of other groups that don't have associated parent bodies. These are typically things like basalts and gabbros and peridotite and mixtures of those. So very similar to terrestrial rocks. So lavas that you get out of Iceland and Hawaii are probably quite similar to some of these. Peridotites like Earth's mantle and some large layered intrusions are very similar to what we're finding from other large asteroids and other planets. We also have the stony ions and the ions. These are mesosideриtes and pallasites. So this is a nice little pallasite at the bottom there. And these are big networks of metal with chunks of olivine in them. And this could be either a case of it's a core mantle boundary that's being recorded from a body that's been completely blown apart, or it's a sort of a really big impact between bodies. And you also get the iron meteorites, which have these wonderful Wittenstatten patterns, which is a crystalline intergrowth of the 2 different iron-nickel alloys. And these are the cores of planets that no longer exist. So there aren't that many parent bodies for achondrites that we know of. We know we've got stuff from the moon, we know we've got stuff from Mars, and we're pretty sure we've got stuff from Vesta, which is the one that I specialize in. So a lot of them don't really have a home. They're sort of free floating in space. So why are there so few known parent bodies? The simple answer is that this early solar system was a really, really violent place. Most of the mass of the asteroid belt is no longer in the solar system. It got flung out as giant planets migrated, as things got blown apart, which means meteorites are key in understanding the early solar system. Without them, there's just a lot of material that we wouldn't even know ever existed, and a lot of processes that we wouldn't be able to record. So that's kind of like a brief introduction to planetary geology as a whole, and sort of puts hopefully a little bit of context for what we're doing and why we study meteorites. And in terms of electron microscopy, because of course I'm an electron microscopist, I work in an electron microscopy lab, this is what I do. There's a couple of different ways we can use EM to study meteorites and help us out in planetary geology. It can be imaging, it can be composition analysis, it can be structural analysis, we can use CL, TEM, TKD's really taken off in the past couple of years. But I'm going to talk about these four because these are the ones that I do and are the ones that are most common for not only just geoscience, but planetary geoscience in particular. So SEM imaging, as I'm sure some of you are familiar with, you can have secondary electron imaging where you're looking at the topography of the sample surface. I don't have any meteorite pictures, unfortunately, using secondary electrons. So this is one of the diamond saw blades that broke as it was cutting through one of my meteorites. I was going to see like the diamonds embedded in the metal there. But what's more useful for us is backscatter electron imaging. This is utilizing the atomic number contrast, which pulls out different minerals, basically. It'll give you an idea of how many phases are actually within your rock. Phases, if you're not a fan of geology words, is just minerals. They're largely interchangeable words. But what we can see is on this meteorite here, we've actually got quite a lot happening. So we've got this sort of like light gray in the background. There are a couple of little variations within that shade of gray. That's a pyroxene. We've got these big sort of like medium to dark gray phases. There's an even darker one in there. There's some that are black and there are some that are white. So we can actually get a good range or a good idea of what's in our samples before we've even done any sort of analytical work on it. Because of course we're doing geoscience and we then take these into doing chemical analysis, we're typically working on polished flat samples. So backscatter for us is really important because we polish our samples flat. There is no surface topography. So secondary electron isn't hugely useful for us. So one of the things we do in the lab quite a lot is large area mapping. And this is an example of a meteorite that we're currently working on. This was found in the Nullarbor in South Australia a couple of years ago, I think by my PhD supervisor, because I don't think I found any in 2018. And this is one of the ones we work on classifying. So meteorites can't be published on or put anywhere unless they have an official name and have been officially categorized. So this is part of the job that we've done. We've got a backlog of sort of 40 or so that we're working through here. And we can see in this large area map, this is quite a big meteorite, it's a couple centimeters across. We can see we've actually got quite a lot happening. You can start seeing different textures, you can start doing different shapes, but mostly you've got lots of different mineral phases, lots of different shades of gray, lots of different bits of white, all sort of dotted around, and it can start giving you a good idea of what you're dealing with. So what we're able to find in this one is we've got this nice big macrochondral. Basically macrochondral is just a chondral that's big. This one's, I think it's about 4 to 5 millimeters across. It's enormous. And that's a whole other problem that we've got to deal with in the future, is trying to understand how that happens. We can also see relic chondrals. So I can see this one used to be a chondral and it's starting to melt. So it's no longer nice and round. It's kind of a bit squished. There's no sort of like real clear boundaries around it. Start seeing some igneous textures. So we can see this nice sort of almost like igneous equigranular textures happening. And you see these nice sort of triple junctions between the crystal grains. That's all very indicative of magmatic activity and melting. And we can also find this line through the middle of it. There's this nice contact between the stuff that has an igneous texture and the stuff that doesn't. So we know we've got more than one rock type in here. So from the backscatter alone, we can give a provisional classification of this rock. We haven't even got into working out what it's made from yet, but we can tell we've got a type 6 to a type 7 brachia. So type 7s in chondrites, they're the ones that are just on the verge of hitting achondrites. They're right on the turning point of the start of igneous activity proper. And the type 6 are the ones just below that. So there's not very many chondrals. It's mostly recrystallized, but there's still a hint of that chondrite nature in it. So from this backscatter map alone, without trying particularly hard, because I remember collecting this one and the focus was not great, but we can see that we've got two distinct regions. We've got these two distinct lithologies, which each have their own thermal history. So we can infer from this meteorite that the parent body had various sort of thermal regimes happening. It was quite diverse, but we've also got mixing from different sources. This isn't a brachia made up of lots of bits of rock from the same location. This has been a mixture of things from different places on its parent body. So there's actually a lot of diversity even in what are considered the most common and most ordinary meteorites. So after backscatter imaging, typically we go into EDS. This is energy dispersive spectroscopy. So it's a chemical analysis using characteristic X-rays. We use the energies rather than the atomic number. And this gives you composition at given points or across an area. So for my genre of planetary science, my genre of geoscience, I use this to calculate mineral composition. So this is pyroxene quad plot. These are the various different end members. Basically this azotype, and that's your magnesium end member. Ferrocellite is your iron end member, and going up this way, you have an increase in calcium. So what we've been able to do is I take my meteorite, I zap all the pyroxenes in it, and I work out what their end members are, and I plot them, and I compare them to literature data for the rest of meteorites. So this is Northwest Africa 6414, it's my current problem child. And you can see it fits on this nice line up through the middle, which matches basaltic eucrites, which is good because it is a eucrite. And if it didn't match, I'd be highly concerned. So this is data from this little cluster over here. You can see we've got that range of minerals happening. So we've got some light grays, dark grays, some whites and some blacks. And then I analyze a different class, which is the same material, but this time it's been shocked. So what we can see is already using EDS is we've got this huge shift in compositions that's happened. So we've got this iron and this calcium enrichment that's dragging these compositions up this way. And this is just a shock effect. This is shock reheating, shock mobilization of elements, and a little bit of shock melting. And it really disrupts and overlaps these igneous trends that we have. And for us, if we're analyzing meteorites, sorry, my computer would like to restart for me, which is a little bit rude. There we go. Shock metamorphism can really disrupt the igneous trends. And if you're looking at a meteorite you've never seen before, and you've got this wide range of compositions, understanding how shock comes into that and what those compositions should have been previously is really, really key. I think that's all that for today. Yeah, so like I said, we can do EDS in a single point or across an area. So this is our little piece of Winchcombe. This is the backscatter map for it. So we've been working on this since it landed pretty much. And if I overlay the EDS map, we can combine different elements to pull out different things. This is a calcium, iron, magnesium, sulfur map. That basically pulling out is the difference in the matrix. So all this kind of like greens and sort of teal colors in the background was what we were interested in this particular one. We've also got calcite in red, as well as some accessory phases. And this is a really, really useful tool to work out where your minerals are, what your minerals are, and if there's any sort of major changes in distribution. So it's a little bit tricky to see, but I've been looking at this map for months at this point. But through this bottom line here, there is a slight difference in composition. There's a slight difference in color and a slight difference in texture. And that's because we've got two different lithologies in our little piece of Winchcombe. And I can't say too much about it, unfortunately, but there is a series of papers coming out in November. I think we're on 5 or 6 different papers, and then there'll be a whole suite coming out based on the individual little bits of Winchcombe from each research group. And we've got a lot left to discover in this. So whenever I mention EDS around other electron microscopists, there's always an inherent sort of groaning that happens because there's a very big divide between EDS and WDS. So energy dispersive spectroscopy sorts X-rays by energy. Wave dispersive spectroscopy sorts them by wavelength. So EDS, generally considered to be qualitative, it's really, really quick to do. It can collect huge data sets very easily. It's very accessible, easy to set up. You can run it from internal standards. There's less work that has to be done to get good data. WDS is a quantitative analysis. It produces narrower peaks, which means you have increased precision and accuracy of your data. So particularly if you're doing sort of things in very low abundances, so trace elements, rare earth elements, that sort of thing, WDS is really useful for that. However, it is slow, especially if you've got a WDS system like we do, where I've only got the one crystal, whereas on an EPMA, you might have 5 detectors running at the same time. What would typically take 30 seconds to run an EDS can be anywhere between half an hour and an hour for me on the WDS system, and it does require regular standardizing. But EDS can be quantitative, and this is the hill I will die on, as my reviewers are currently well aware. So this is an example of some WDS versus some Quant EDS data that I have for meteorite I'm currently working on, and I'm getting through review at the moment. So WDS is in blue, Quant EDS is in orange. You can see on these graphs, there's not really a whole lot of blue visible, because Quant EDS can be comparable to SEM WDS if it's used correctly, and it can be really, really powerful, as well as helping you generate much larger sets of data with limited beam damage, and also make it much more accessible for a wider range of people. So if you do want to collect good Quant EDS data, you have to make sure your sample prep is good. I outsource all of mine to my colleague Cheska. She's never given me a bad sample. Everything is beautifully polished, beautifully prepared. But if you have any sort of surface topography, that's going to upset your beam. You have to ensure that your beam is optimized on the pure sample at the same operating conditions you're working at. You can't change anything. Once you've optimized, that is what you're analyzing at. You need to make sure you have a good beam stability as well. So the system that we use downstairs, our JOL 7001, that has a beam stability of less than 0.1 nanoamps across 3 hours. And your operating conditions that you're working at, you need to make sure that they consider the overvoltage, so you're making sure that you've actually got enough energy to measure all the things that you're looking for, but also that your dead time is appropriate for your EDS detector. And it may be a case you can jiggle it around, you can retract your EDS detector slightly, you can change the working distance slightly. It takes a little bit of time to work out the best operating conditions for your particular system, but it is definitely worthwhile doing in order to get good data that is representative, but also comparable to WDS quality. You keep your standards up to date. As your instrument gets older, the beam decays, or as things change in the surroundings around it, and you make sure your standards are up to date. I try and do them every 6 months here. It takes about 3 days of my life because we have a lot of instruments and about 4 different standards blocks I need to get through. And it's important as well to utilize standards that are similar to the material that you're analyzing. So if you're analyzing metals, you would use standards that are similar to that. I work on minerals, so I use a set of mineral standards so that they are similar to what is being analyzed, so the software has a better chance of actually unraveling it and making sense of the data. So that's kind of like my little spiel about Quant EDS, because I think it's a good technique, and I think it's proven itself, especially in recent years. There's been a lot of work by the guys over at NIST, the National Institute for Standards. There's been lots of work by other researchers as well as the manufacturers of the EDS detectors. So it is a good technique. And if anyone does want references and citations around that, let me know. I've got a whole list of them. There's some really, really useful things out there. A newer technique that I've recently taught myself how to do is electron backscatter diffraction. So this is using the crystallographic structure, so the orientation of your different minerals, to look for evidence of foliation, lineation, crystal settling, magma flow, deformation that happened post-crystallization. And this one is a little bit more complicated because you have to tilt your sample to 70 degrees. So again, having good sample prep is really important. You need a flat surface, otherwise it's not going to be in focus as you scan across the sample. Also, just making sure your sample is really well stuck down so it doesn't fall off inside the instrument is vitally important. So we can produce a range of plots. So you can sort of look at different alignments. So these are 2 different ansatites from different meteorites. You can see in this top one, everything was pointed the same way, so you've only got this one hot spot. In the other one, there was a little bit more variation. So we've got lots of different crystals facing different directions, so you end up with lots of different spots. I can also produce maps like the one in the background. And importantly, this is vastly underutilized in planetary science. EBSD has come on a long way, and it no longer requires the amount of sample destruction as it used to. So there's a couple of groups that are doing some really, really good EBSD work in planetary science. There's some of my colleagues in Australia produced a wonderful study about lava flow and mineral settling on Mars using meteorites and EBSD. So there's a lot of potential for this particular technique moving forwards. So how do we tie it all together? The next couple of slides are going to be sort of like a little case study of what I'm currently working on, including some data that I got last week and haven't had time to understand yet. So this is one of the meteorites I work on currently. This is Northwest Africa 2968. It is a tiny, tiny little piece of what we think is Vesta, the danitic diogenite. So it's basically a couple of grains of olivine, nothing much else in there. And we can see it's got like these nice big sort of like black veins through it. These are all shock veins. So we know it's been shocked. And from the thin section, we can tell it's got mosaicism in the extinction. That's another indication of shock. So this has been pinged off the parent body with some significant force. So the goals really for me is to identify microfeatures, mineral compositions, and petrofabrics. And this is part of a larger study where I'm going to compare a lot of different diagenites to other meteorite groups as well, and hopefully try and get a little bit more information about what these things actually represent in terms of real geological rocks. It's a large area backscatter map. You see there's actually not very much happening in there. There's extensive metal veining, so all this white stuff through there, that's all metal. It's an iron nickel metal, and you can see it's pretty well throughout the entire sample. But importantly, there's little to no variation in silicates. There's all the same shade of gray in the background there. And if there were any like major compositional changes, you would see that. So you can see this sort of like lighter patch around the edge. That's a slightly different silicate, but this main bulk is pretty unremarkable in the long scheme of things. Go into the EDS, and we can see, yeah, it's still pretty unremarkable in terms of composition. It is a consistent olivine, so that nice green color in the background there. No obvious changes in composition in that. I do have some individual point data, and this rocks up to about forthright 91. It ranges everywhere from, I say everywhere, it ranges from forthright 89 to 92. The average is about 91. So if you imagine a scale of basically 0 to 100 of how magnesian it is, it's a very magnesian olivine, which is unusual for HEDs, and that's a future problem that I will deal with. Got a little bit of pyroxene around the edge and a couple of localized spots in the middle. It got some small bits of chromite, a little bit of feldspar, little bits of troilite, and this metal throughout. So accessory phases are somewhat localized. They're not sort of everywhere. There's actually quite a couple of areas where it's sort of just olivine, it's just silicates, which is useful for the sort of stuff that I'm interested in doing. So this is the new data I was talking about. This is an ESD map. This is an inverse pole figure map on the z-axis. And again, so in this one, all the different colors relate to different crystal orientations. So those big olivine grains are basically all pointing in the same direction. As you can see on this little plot here, there is basically nothing really happening in this rock. Despite all the shock veining, it is pretty unremarkable. There are these localized bands of recrystallization where things get a little bit more wonky, and these are all associated with those big veins of metal. And this is all basically sort of shock recrystallization, which is largely typical in meteorites. Importantly, we couldn't see these tiny little crystals in the EDS. If I flick back up to the EDS, there is no obvious change in composition. There's no obvious grain boundaries, but it does exist there in the EBSD. A little bit of misorientation up at the top here, that's slightly lighter blue. But again, really unremarkable rock. Another way we can show EBSD data is using a Grod angle. This is a grain reference orientation deviation. So this is looking at misorientation in an area compared to sort of like the local orientation around it. So these bits that are green are showing higher strain than these bits in blue. So we can see we've only got, it's mostly sort of like this sort of tealy to green color. So we've really only got sort of orientations pretty much up to about 15 degrees in this sample. There's a couple of little hot spots where you get a 40-degree rotation. But again, it's pretty unremarkable. So despite all those bits of shock veining and the amount of metal that's been pushed through this thing, it's largely unaffected by shock, which is really, really cool. What I have noticed is that some of the strain seems to be oriented. This is kind of like this northwest, southeast sort of trend sort of happening through here. So my next job is to actually work out what that means, because I have no idea at all. I need to reconcile that with other EBSD data, what that means in terms of igneous processes, and unravel that from shock processes. So it's going to take a little bit of work, and I'll then be able to compare that to other Dargenites and to establish a provenance on Desta. So what does this mean in terms of actual geology? So you've got a load of EM data. What do you do with it afterwards? What I typically do is I take it into compositional modeling. So I've got all the EDS data, it tells me what the minerals are made out of. I can put that into a compositional model, and I can extrapolate outwards and try and run things backwards, work out where things have come from, where things are going, and how it relates to other meteorites. You can also do thermodynamic modeling. So you take your compositions, you work out all the different factors that go into the physics of it, and you can look at how do these things melt, how would they behave at different pressures, different temperatures, and produce phase diagrams, which is a really, really useful thing in geoscience. You can also combine it with other analytical techniques. So lots of people do EM data, they then do isotopes. And the main thing is to make sure you do your electron microscopy first, because it's a non-destructive technique. The amount of times I have students come back with rocks and they've got these beautiful thin sections that are covered in laser ablation holes, which then means we can't do things like EBSD because we're recrystallizing around the laser ablation. Or if you need to grind anything up, make sure you do your non-destructive stuff first. And we can then use all those other models, all that EM data, and we can use this to basically work out what geological processes were happening on other asteroids and planets billions of years ago. And what does this mean in terms of planetary growth and evolution and things that we otherwise wouldn't be able to work out or to be guessing about. If you would like to see us do electron microscopy on meteorites live, at the end of this month, Microscopy Live, which is my outreach event, Cheska and I will be analysing our favourite meteorites in real time, so let's see what it is that we do. And guarantee something will be from Mars. It's a little bit more exciting than the stuff that I work on, as you can see. So it is free, it's live and recorded, so pop on over to our website and you can sign up then for more information. And that kind of brings me to the end. So it's quite a short Imaging Matters this time, mostly because I've been busy doing my analysis rather than making presentations. But electron microscopy is immensely powerful, and it has huge potential, and particularly the uprising of EBSD, there's a lot left that we can do and a lot of things that we can reanalyze using EBSD and fill in some gaps in our knowledge. Space isn't going anywhere, and meteorites are landing all the time and new ones being found all the time. So there's always something new. And I've yet to find a meteorite that has nothing interesting in it at all. There is a lot of tiny things that get recorded in places where you don't really look. And there's always something new, something we can add into our understanding of solar system chronology, or how lavas work, or how chondrites get stuck together, or how melting happens. There's so much that we still have to work out. And it's good fun, mostly. But that's kind of it from me today. I would love to answer any questions that anybody has, be it about space or about the techniques that we use. And yeah, thank you very much for listening.
Okay, thank you, Jem. Wonderful as ever. So does anybody have any questions first up? Okay, well, that means if nobody else has, I'm going to have to revert to one I've got, and as a biologist, it's going to be a really stupid question. So my question is, and it probably is a really stupid question, but we'll go with it anyway. So the meteorite that you look at, once it's fallen to Earth, it's gone through quite a process between going through our atmosphere, the amount that's burnt up, the impact when it hits the ground. How biased do you think what you're looking at is, or how representative of it do you think it actually is of that parent body? How, because I would imagine that, you know, certain minerals are more likely to break up and burn up in the atmosphere than others. So whether that then biases what you're looking at?
Yeah. So one of the main issues we have with meteoritics is that 90% or so of meteorite burns up in the atmosphere. So what you're actually left with is much smaller than what it started off being. On top of that, you have, depending on where that rock's come from on its parent body, will skew things. So I think there was a study that came out a couple of years ago that estimated that from Vesta, this big 500-kilometer asteroid, in our meteorite collection, we've probably only got 3 to 5 impacts actually recorded. And Vesta is covered in craters. There's a lot of material that is out there somewhere or fully gone. And what that is recording might be very different from what we see in our rocks. That's why I do a lot of work on brachias, so rocks that are made up of lots of different bits of different lithologies stuck together, just because you get more rock per rock that way. But yeah, it's very much a case of meteorite survival when they land as well is a thing. So if you remember the Winchcombe meteorite last year, when that landed on someone's driveway, it just disintegrated into dust because it's basically mud. If you have an iron meteorite that comes through, like these are big chunks, they're tons in size. And there's definitely a skewing of how much material you get versus compared, basically depending on what sort of meteorite class it is. The stony meteorites typically survive okay. A lot of them are crystalline, they're not particularly porous, so they are actually held together pretty well. We always treat them very carefully in the lab and we try not to drop them, but again, they've fallen from space. They could probably stand to like fall off my desk and that'd be fine. But yeah, there's definitely, I think, there is definitely a bias in what is recorded and what people find. And it's basically a case of just find as many meteorites as possible, analyze as many meteorites as possible, and hope it fills in some gaps. And the rest of it we can extrapolate outwards.
Yeah, I guess just add to the database as much as you can.
Pretty much.
Everything adds to existing knowledge, I guess.
Yeah, and there's tons of thousands of meteorites that have been classified. There's just been an ANSMET, the Antarctic Meteorite Survey, that they've just had a load classified. It's like hundreds from them. So I think there's been about 2,000 new meteorites this year alone.
Wow. Okay. Cool. Has anybody else got any questions?
Yeah, if I could ask Jen about calibration.
Yes.
You talked about having some standards you used every 6 months or so to calibrate. How many different materials do you tend to use in the calibration? You talked about half a dozen or 40. So I've seen both numbers bandied around.
Yeah, so we use a series of MAC standard blocks, microanalysis consultants based up in Coventry. So we have a couple of custom made blocks from them. Typically, if you have one of their, I think it's the 37 block, is one of the standard ones. You can get that from a couple of different suppliers. MAC are local and they are pretty well priced. A 37 block should contain pretty much everything you could possibly ever want to come across. The benefit of sort of doing standardized EDS is once they're in the system, you can just use them repeatedly. But I think depending on what you're looking at, so our rock forming minerals block, I think, is only 16 samples. So if you know you're only going to be looking at certain things, you can buy standards blocks that cover you for those things. If you don't need to be measuring rare earths, you don't need to buy a rare earth block, if that makes a little bit of sense.
Oh yeah. And what do you coat your materials with for EDS? You use carbon or gold or what?
We use carbon. So carbon is electron transparent. If you want to do composition analysis, it has to be carbon or uncoated. So we aim for 10 to 15 nanometers of carbon. Getting a thin coat is pretty important. Having a good understanding of how your coater behaves and what thickness you're coating to is quite important. Carbon does suck up X-rays from light elements. So if you're trying to measure oxygen or even sort of like aluminium, if you've got a thick carbon coat, it can actually be quite difficult to get good values from it. So understanding the best conditions for your particular carbon coater is very key to making sure that the data you're getting is actually correct. So I think we use a core M1. I think we're coating to about 15 nanometers at the moment.
Thanks. And what happens if you coat with gold or?
You will measure gold.
And nothing else?
Nothing, not really, no. You'd have to put so much power into the sample to get through the gold coat. Because gold's quite heavy. Again, it's going to suck up a lot of the X-rays. So EDS is a carbon coating technique.
I feared as much. Thanks very much.
That's right.
Okay, anybody else? I'll take silence as a no.
That's fine, it means it's lunchtime.
It's definitely lunchtime. Well, thank you everybody for coming.
Thank you very much.
Thanks to Jen for the presentation. And we will be back again. Watch out, and I'll put it out on social media and email as soon as I've determined exactly who it's going to be. But we will return again. Thank you all for coming today, and we'll see you again in the future.